Okay, welcome back. Well, this is ThinkTech Live. We're talking here on the SOEST Hour, the School of Ocean and Earth Science and Technology. And thanks to Talia Ogliori, we have some great guests from the College of Natural Sciences, which is actually not in SOEST. That's the magic of SOEST. It draws people from outside of SOEST. SOEST is friendly. It's a community of people inside and outside. Am I right?
Yes, of course.
Okay. Then we have Leung Ng, who is the a professor of chemistry at the College of Natural Sciences, and Cisco Jimenez, who's a PhD candidate working with Professor Ng. Thank you for coming, you guys. Welcome to the show.
Happy to be here.
So we're going to call this today Locating the Hydrogen Atom in Protein Crystals, which, I mean, my wife and I speak of little else at dinner. Yeah? I bet you do too. So tell us, Professor Ng. What is the training? What is the life path that got you to where you are here now at ThinkTech Talks in the studio?
Oh, well, that's actually interesting because my path is certainly not the conventional one. To start with, unlike a lot of other people here at the university, I actually grew up in Hawaii. And somehow, after 20 years, I found myself back in Hawaii doing research and teaching. I was an undergraduate at Harvard. I studied biochemistry there. And originally, I had planned to be a medical doctor. And then I went to UCLA to pursue a MD and PhD degree and found out that what I loved most was actually the chemistry and physics aspect of medicine and biology. So from there, I followed my dreams to pursue a career in research. I moved to Berkeley, and then after a short stint at a biotech company, I ended up here at UH.
I have some questions. Cisco, can I ask him a few questions?
Of course.
I'll ask you questions too.
Yeah.
So, Harvard, okay? Local boy goes to Harvard. What did you do to make that possible? Was that hard work or good looks?
Can't
A little
say
bit
it's
of both,
good
I
looks. I think I had always set high goals for myself, and I was always a very good and passionate student. I always loved what I did. I loved studying, and I loved learning more than anything else.
And UCLA, also a very good school. What was attractive to you about UCLA?
I really wanted to move to the West Coast. I liked the climate, the weather in the East Coast was just too much for me, and I wanted a more relaxed, friendly environment than what I found in Boston.
Including the weather. Yeah. So, and now you came back. What made you come back to Hawaii? Were you always looking to come back, or was there some event, some opportunity that made you come back?
Both. So actually, I had never seriously thought about coming back to Hawaii because with a career in the sciences, there isn't that much here compared to the hub cities like San Francisco or Boston. But it was always in the back of my mind, and every year or so, I would look at the UH website and see if a position came up just for kicks. And one year when I was actually looking for a new job, it turned out that there actually was a position looking for someone doing exactly what I'm doing, which is the field of biophysical chemistry. And at the same time, for family reasons, it was the perfect time for me to come back. I was about to have our first child, and so my parents still live here in town, so it was just perfect that my daughter could grow up here in Hawaii with grandparents and extended family.
One last question, and we go to Cisco, is this. So many people say in science that there was one teacher, one course, one moment, one influence which directed them toward this science, which made you love the science you do, which is, is in chemistry and medicine, if you will, and biology, that area. Did you have a moment like that, or a teacher, an influence that turned you in that direction suddenly?
Not suddenly. Actually, I had always loved science even since I was a little kid. And I think that's natural for a lot of little kids. Kids are curious about why the sky is blue, about birds and rocks and the water. And it's just that oftentimes they're not given the nurturing and the guidance to feed that interest in science. But somehow I was able to sustain my interest through the years. I think for me, probably the biggest influence from a teacher was a chemistry professor I had at Harvard, Martin Karplus, who actually received the Nobel Prize this past year. He does research applying physical chemistry methods to problems in biology. And I like that kind of powerful quantitative thinking to attack the hard, important problems of biology.
Mm-hmm. You know, we're going to have a fellow named Peter Greenwood. He's a medical doctor researcher in one of our programs at the end of August on medical research. And I remember interviewing him before. He said that was a fork in the road for him, whether to be a PhD researcher like you in medical things, mm-hmm. or whether to be a doctor researcher. And for him, the difference was how much grant money you could get, honestly, is what he said. So, I mean, I wonder what, you made that same choice, except you went down, you could have been a doctor researcher, that much, that was as easy, or you could be a PhD researcher. Why did you pick PhD research?
It was closer to to my scientific interests in the physical sciences. And also, I think I like the path of yes, there's certainly those problems with the grants and supporting your science, but what I like about the career of a purely academic researcher is the independence and creativity that we have to pursue the ideas and the problems that we think are the most important. In the medical field, for obvious reasons, because you have to take care of your patients first, you can't take risks with your patients. There are a lot of very important ethical boundaries, and obviously you can't do experiments with patients as easily as we can do experiments with microbes or chemicals. So it was a good fit for me.
Interesting. What high school did you go to?
Iolani.
Oh, okay. Yeah. You have the look of it in the Iolani. I spent a fair amount of time down there. Okay, Cisco, how did you get here? I mean, how did you get into what you're doing?
I had a kind of a different route than most people as well. I am kind of an older student. I returned to college after many years of working, and it was just blind luck that I ended up with a job in a chemistry-related job at a metal plating plant, and that kind of got me hooked into the sciences, and so I went back to college to get my BS degree, and while I was there, I did really well because I think I was just older and more focused now.
Not true. That happens to people. Have a few years out on the economy, teaches them so much.
Yeah.
And they get to appreciate, the power of making life decisions.
Yeah, I agree. I kind of lucked into an internship with Genentech in San Francisco, mm-hmm. and I did a lot of computational work there, and I just fell in love with the whole field, the work that I did. It was a lot of protein computational chemistry.
Can you describe what that is so that the average person will know? I get the feeling that computational means computer.
Right. Yeah.
Database,
so what we do is basically use math and different theories, and then we take real data and we kind of make a really good educated guess on what this data can tell us without actually having to do real experiments, which can be kind of costly. And so a lot of pharmaceutical companies are moving in that direction these days because it saves a lot of money. It's a lot cheaper to run a computer than to run a whole series of experiments. And so that was kind of what I focused on there at the internship.
And just P.S., that's what Peter Greenwood found. He was first sending them, the big pharma companies, actual blood and serum for their databases for them to experiment on. And then he realized that if he divided the blood and serum into fields and described it by fields, lots of fields, lots of fields. All he needed to do was email them the database, and they could use that in the same way.
Mm-hmm.
That's something. That's the world of high tech today. Sorry, I interrupted.
No worries.
So okay, so how did you get out to Hawaii? I mean, what took you out here? What appealed to you? What made that possible?
Well, I was looking at a few different graduate schools, but I was actually really interested in the work that Dr. Ng was doing.
So you came to Hawaii for Dr. Ng?
Partially, yeah. I mean, partially, I just wanted to come to
That's
Hawaii.
the right thing to say if you're working for him. You know?
Yeah. It was.
We didn't rehearse
The
this.
work he was doing looked really interesting to me when I came across his faculty website.
Okay. So there's two examples of people on the mainland looking at websites, checking out what's going on in Hawaii.
Yeah.
So I mean, is this a good career move for you? Is this going to take you to new levels, or is this more like sort of a spur? I mean, professionally for you.
I'm hoping I can turn it into something that'll be good for me career-wise. I mean, the research that we're doing is right in the area of expertise that I want to develop for a career later on. And so a lot of this stuff is at the crux of what's happening in industry, and that's kind of where I want to head someday eventually. So, I see this as really being a potential benefit for me.
Where do you want to head?
It'd be nice to get a job at a large pharmaceutical company doing drug design research, cancer meds and things like that, because then I'd have the benefit of being able to do the research I want and still have a decent income.
Yeah. It'd be nice if we had companies like that are doing research here. I remember when the medical school in Kaka'aka was first established, the dean was Ed Cadman, great man. And his vision was to have big pharma all around the medical school. There was land there. And it's a campus of big pharma doing exactly what you're talking about, but that didn't happen. Maybe it still could, but I wouldn't make bets on it.
It'd be nice.
It'd be great.
Yeah. Well, so so tell our audience, what it is to do research in chemistry from your point of view, from the point of view of a PhD, assistant.
I guess it would really depend on the kind of research you're doing. In my case, there's a lot of computer work involved, of course, because it's a computational project. So I do a lot of programming, a lot of math. There's a lot of math involved in what we do. And then we get to do some experimental work too. So I get to be in the lab and I get to grow bacteria that will make the protein I need, and then I can take that and purify it and grow crystals from that, and then hopefully send it to a Stanford synchrotron where they can shoot X-rays at it and I can get some data to use.
Oh,
That's the long-term
Was this
goal.
what you were doing before, or is this something that's unique to
This is something I've never done before. The experimental side is all new to me. So Dr. Ng's really helped me a lot with that. I'm really grateful for it.
Is this something that, going back to the, being on the mainland and looking at the internet, is this something that's going on elsewhere? Did you have choices here, or was this the best place for you?
There's always choices. This is a really good place for me to be right now because I get to do all of these things, and what I really like is that Dr. Ng has given me a little bit of freedom on the project, which I might not have gotten other places. So it's been really, really a good experience for me.
Okay, so you work together where on the campus? I just want to visualize.
We're in Bilger. Do you know where that
Bilger
is?
Hall. Okay, and you have laboratory there, and it's a combination laboratory, I take it. And one is you're actually doing
Right.
chemistry,
Experimental.
old-fashioned high school. Pardon me, old-fashioned
Not old-fashioned.
chemistry.
Cutting edge.
Cutting edge. And then the other is the computer aspect of it.
Right.
Okay, which is that in the same place or is that in a secondary place?
It's kind of split up. We just expanded, so we have 2 labs now. Our group is growing very fast, which is a good thing.
How many in your group?
I think last count was 13 or 14.
Oh, this is a major operation then.
It's quite a few.
And you're
Ramping
the
up.
principal investigator on
Yes.
this. Oh, exciting. Okay, we're gonna find out more exactly what you do in these labs right after this break. This is ThinkTech. We're here at the SOLIST Hour. We're talking to Professor Leung, who is professor of chemistry at the College of Natural Sciences in Manoa, and Cisco Jimenez, who is a PhD candidate who works with him. We're calling this show Locating the Hydrogen Atom in Protein Crystals, which we're going to discuss in detail right after. So get your pens and paper out so you can actually write down what
There'll
you're
be
doing.
a quiz.
There'll be a quiz, thank you. Yeah, this is not simple. We never promised you a rose garden. Okay, be right back. Okay, this is ThinkTech, and one of our favorite shows is Hawaii, the State of Clean Energy. And it goes 4 to 5 every Wednesday right here from ThinkTech in Pioneer Plaza at the core of downtown Honolulu. And my co-host is Ray Starling from Hawaii Energy. Ray, do you like the show?
I love the show. It's great to see all the new people coming in with new ideas about how to save energy, get us off of fossil fuel, and that's what it's all about. So Hawaii, the State of Clean Energy. See us on Wednesday afternoons at 4 o'clock.
I knew he'd say that. Thanks, Ray. Okay, we're back at the best part. This is the SOLIST Hour, the School of Ocean, Earth Science and Technology, where we're having some visiting research academics from the College of Natural Sciences today. We're talking to Leung, who's professor of chemistry there, and Cisco Jimenez, who's a PhD candidate there. We're talking about locating the hydrogen atom in protein crystals. So, as we always say on this show, gentlemen, talk your own language. Talk the language of science, and they will figure it out.
Okay.
Put them in your, in your world. Okay, tell us what you are doing. Okay.
Okay. So what we're interested in is understanding the structure of proteins. Now, for a lot of people, when you hear the word protein, you might think of protein in your diet. But actually, protein is the primary component of all of biology. So your bodies, other than the water, is primarily made up of protein. And it's the proteins that give our bodies structure that allows all the different chemical reactions to take place in our cells that are needed for life. Many diseases are caused by when proteins malfunction. So there is tremendous interest in understanding how proteins work. That way, for drug discovery, we can develop drugs that are very targeted towards the specific molecular defect that drives the disease. Now, to understand how a protein works, we need to understand its structure. So a protein is a molecule. It's a very large molecule, but it's a molecule made up of atoms. So how do we see the structure of something so small? Now, with a microscope, you can look down to the level of cells and bacteria, but you reach a limit, a hard limit, because when you want to look at something as small as atoms, you're looking at something that's actually smaller than the wavelength of light. So you can't do that. You need to introduce new types of techniques. The technique that we use experimentally is called X-ray crystallography. So what we do is we produce the proteins that we're interested in the lab, primarily through using microbes like bacteria or yeast to produce these proteins. And then we try to grow microscopic crystals of these proteins. We fire X-ray beams at these crystals. We collect the data that comes off of the X-ray interaction with the atoms in the crystal. And from there, we can deduce and see the actual atomic structure of the proteins. But there's one thing that's hard to see, and those are hydrogen atoms. For those of you who still remember your periodic tables from high school chemistry, hydrogen atom is element number 1. So it has 1 electron. It's the smallest atom. So because of that, it interacts very weakly with X-rays. So when we get this X-ray data, we can it's very, very difficult to see the hydrogen atoms. And they make up almost half of the atoms in a typical protein. Now, if we can't see where the hydrogen atoms are, then we can't get a really good understanding of the structure, the total structure of the protein, and how it works or how it doesn't work in the case of disease. So what we're doing is developing new methods to try to look deeper into the data that comes off of the X-ray, the experimental X-ray data, using computational methods that we're developing to try to predict the location of these hydrogen atoms.
So a couple of questions come to mind. There'll be more, but one is, I remember Superman had something to do with crystals at the North Pole.
Do you know this?
Superman,
His Fortress of Solitude.
I know Fortress of Solitude. What did he have to do with
It was
crystals?
built out of ice crystals. That's all I know.
There
yeah.
you go. I need to know what a crystal is. I need to know how to make a crystal. I need to know why you need a crystal for this kind of work.
So a crystal it's a solid where the atoms have had lots of time to organize themselves very well. So they get into this really, really nice ordered structure. And the more ordered they are, the better quality the crystal. And the reason we want that is because when we shine the X-rays at it, we're using the crystal as kind of a diffraction grating in a way. So what that's doing is when the beam of light hits it, it's splitting the light into a pattern that we can then use, and we can read this pattern of spots and translate it back into 3 dimensions.
The crystal literally amplifies the signal that you get from of the molecule, because the molecule is repeated millions, billions, bazillions of times in the crystal lattice. It amplifies the X-ray scattering that comes off of that molecule.
So it has surfaces,
Mm-hmm.
and it's the surfaces that return the light. Or the
No,
X-ray.
no, just actually it's not the surfaces. It's just the packing, the regular packing of the molecule in the crystal.
Okay, and they're packed differently in the crystal than they would be in natural form.
Right. So
Well,
that's why water floats when it's ice, because it's been packed less densely than when it's in its liquid form.
Okay.
So the molecules are all jumbled together when it's wet, when it's a liquid. And when you freeze it, they get really ordered and they line up so that they're spaced further apart. So then the ice then can float.
So, Zuri, why don't you tell everybody what we're doing with ThinkTech High, and if they want to ask questions, because I want everybody to know this because of the exam. It's because of the exam. Okay.
So if anybody would like to actually participate and ask questions or interact with the show, you can always tweet us at ThinkTechHI on Twitter. You can find us on Facebook at ThinkTech Hawaii, or you can always contact us directly through www.thinktechhawaii.com. We'll be happy to work with you. Thank you.
Okay, that's Zuri Bender. Terrific. She's our floor manager and our studio manager. Well, okay, I'm trying to figure out what people would want to know if they were listening. So, and how do you actually make the crystal? What is the procedure for that? Is there a machine that does it?
So that's kind of the million-dollar question, because making crystals from protein isn't always straightforward. So there's a lot of different ways you can approach it. But oftentimes we use a robot to try conditions in 10, 12, hundreds of different little wells that we put protein in, and then we try different things to make it crystallize.
So it'd be different for one kind of protein or another?
Correct.
It's not the same thing each time?
And it's unpredictable.
Very different. Yes.
Unpredictable.
This is a little bit of the high school chemistry. You're just mixing your protein with all kinds of different combinations of chemicals.
So you're also learning how to make crystals here. Is that part of the research?
Yes, it is actually.
Because you're different proteins and so
Yep.
forth. Now, you mentioned that the hydrogen element molecule was small, even though it's why did I always think that the hydrogen element, oh, I know. I thought that the hydrogen element was big because there's more of it,
Yes, it's the most
Lots of it.
abundant
Yeah.
element in the universe,
but it's small, actually.
but it's the smallest atom.
Yeah, so why do you like working with hydrogen if it's the smallest one?
Oh, because it's the unknown. As a researcher, and this is the fun part of doing research, is that you're always looking for important questions that are not solved yet. And if everyone is looking and studying there, then that's not what you want to do. You want to find somewhere else and something else to do.
That's like news gathering, too. Same thing. You want to bring to them something that nobody knows about.
That's right, yeah.
Yeah. So I mean, I asked Cisco this, but I mean, are you unique actually? Are you doing something that nobody else is doing?
Very well. This specific problem, I believe, we're pretty close to unique. There are some people approaching this experimentally, using different types of biophysical experiments to locate these hydrogen atoms. But our approach is unique.
If you make something into a crystal, can you unmake it back into its original form? Is it like freezing it and then unfreezing it?
Sure. Yes, definitely.
So you can take this into a crystal, you can do stuff, look stuff, move it around, whatever you want to do, check it out, and then return it back
Yes.
from whence it was. How do you return it back?
So I guess it depends on the nature of the crystal. If it were, say, a diamond, it'd be very difficult. But for water, you could just let it sit and it will melt back into water. Or for a protein, you can put it in some kind of solvent that will redissolve it back into a solution.
Huh, okay. Could it be dangerous? I mean, you say you're working with bacteria. Could that be dangerous? You have to wear gloves and everything?
I mean, you should wear gloves just because it's good laboratory practice, but most of what we work with is very, very safe, not very dangerous.
Garden variety
Yeah,
proteins.
very standard.
Okay. All right, so now the question is the X-rays. So you're flashing X-rays on this crystal, and you want to see what happens. So I can't imagine exactly how you do that, and what comes back, the return that comes back from the X-rays, and how that makes sense to you from a research point of view. Can you talk about that?
So what we do is we take these crystals, and these crystals are extremely small. They're usually barely visible by the naked eye, so less than a millimeter in size. And we typically do these experiments at national lab facilities on the mainland. So these are very large billion-dollar facilities, of which the United States has about, I believe, 6 of these. So these are synchrotron facilities, particle accelerators that generate the intense focused beams of X-rays that we need for our experiments. The X-ray beams hit the crystal, and they scatter off the crystal. The scattering pattern that comes off of the crystals are measured, and then we have to assemble these scattering patterns using different types of software and convert them back into basically the atomic image.
So how do you read the scatter? Is there a device you use?
Yes, actually it's quite similar. A lot of it is similar to that used in your consumer cameras. It's a CCD, charge coupled device detector. So the X-rays are photons, just like light for your cameras. And then you use detectors that pick up these photons.
Okay, so now what do you get? I mean, can you see what you're getting, or is it just a bunch of numbers?
No, you see what you're getting. You basically get a bunch of it's hard to do this without visual aids. Maybe I should have brought some.
That's okay.
You should.
Just a word picture.
You get a bunch of spots that look like that are arranged in rings, concentric rings around the central point.
Kind of
Okay.
like a bullseye kind of.
Yeah, okay, that's good.
Kind
But
of.
like a
no
bullseye.
two bullseyes are the same. And they hold different characteristics.
Right.
And it's the characteristics of the bullseye.
Right. So what
that
we're
you're
doing
looking
is
at.
that we want to measure the intensity of each of those spots, the geometry of each of those spots to the other spots, and we assemble them. So typically, for your average protein crystal structure, you would have tens of thousands of these spots.
Okay, we're going to talk more about that right after this break. That's Professor Leung. He's professor of chemistry at the College of Natural Sciences. And to his left is Cisco Jimenez, a PhD student working with him on locating the hydrogen atom in protein crystals. What an exciting discussion. This is the SOS Show. I'm Jay Fidell. We'll be right back.
Hi, I'm Donna Blanchard, and I host the show Center Stage on the ThinkTech Hawaii digital series right here every Wednesday from 2 to 3 Hawaii time. I would really love to have you watch the show and see what we do here. I talk with some of the most amazing people, artists, most of them, all of them involved in some sort of artistic process. And our goal here on the show is to dig into that artistic process, and you would not believe what some people say, what some people do, what people go through to express. And these are people who have to express somehow, and I find that infinitely interesting. Not only that they have to express, but how they end up doing it. I really hope that you will watch the show and enjoy talking with some of these people the same way that I do. Thanks, and I hope to see you soon on Center Stage on the ThinkTech Hawaii digital series, Wednesdays from 2 to 3. See you soon.
Okay, we're back. We're live. I'm Jay Fidell here on the Monday 1 to 2 block in the SOS Tower, School of Science and Ocean. What is it? Science and the School of Ocean and Science, Ocean and Earth Science, Ocean and Earth Science and Technology. Okay, and a friend of that school is the College of Natural Sciences, and we have Leung and Cisco Jimenez here to talk about locating the hydrogen atom. So we have these concentric circles that come out when you read. You know, the bounce back, I guess, of the X-rays that you're shining on the crystals that have of the proteins that you're looking at. Okay, so and I guess no two concentric patterns are the same. So you now I get the feeling that you're going to go from those concentric patterns to making some sense out of it on a computer.
Yes.
How do you do that? You measure the characteristics of the concentric pattern.
So that's actually kind of a lot of work, but there are a lot of computer programs now to help turn that weird scattered pattern into a three-dimensional structure, and that's kind of where most of the structural data comes from. And so you can use programs to do that, but what we're more interested in is once we have the structure, they're usually incomplete because they're missing half the molecules. Those hydrogens are basically invisible to X-rays. So we can get the structure, but we have to guess basically where all the hydrogens are. And a lot of them, it's really easy to guess. We can know pretty well where they're going to be. But a lot of the other ones we're not so certain about. And so that's kind of the focus of our project. And it turns out that the ones that we're not so certain about tend to be some of the more important ones in a lot of cases. So it's not always the case, but often it'll be a certain hydrogen that's in a certain position that can make a drug much more effective. And so kind of the end result that we're hoping for is to make it easier for scientists to have a better guess at where these hydrogens are so that when they're designing drugs, they can make them more potent, more effective, less side effects. That's kind of the future.
So that's the relevance of this work, that it is going to help some pharma company design drugs.
Right.
And the missing hydrogen atoms. I
Yes.
guess, the missing hydrogen atoms are somehow a key to
Yes.
building better drugs.
In a lot
Absolutely.
of ways, yes.
You know, just describe one way. I mean,
Right.
if I'm building drugs, I imagine a long formula. It's a compound, right?
Right.
So it's very complex compound. You wouldn't find it in nature probably, and it has lots of elements and lots of atoms and different proportions. And then, of course, there's the process of how you put all that together
Absolutely.
into the compound.
And the difference between a successful drug and a failed drug can really be just one atom.
Okay, so I'm a big pharma company. Talk to me. Tell me why your work is critical to my building better drugs.
So with modern drug discovery, we take, at least for what is known as target-oriented drug discovery, where you have a specific protein target that you want to design a drug against. You want to know the structure and the chemical properties of that target. So once you do that, so let's say we pretend that this is your target, then you design a molecule that fits right here and sticks right in the part of the protein that you want to block. So that's why knowing the exact precise structure, atomic structure of your target is critical, including the hydrogen atoms, because those hydrogen atoms can interfere or complement the binding of your drug candidate molecule.
So it will work better.
It could.
So what does that mean, work better? And how does a hydrogen atom or not affect it working better? I love this stuff. I didn't know anything until we started this discussion. Thank you.
Well, what's interesting is, so proteins are very big, but most drugs are actually pretty small. And so you can think of it as kind of like a lock and a key in a way, right? It's a very simple way to think about it, but these keys, you can make them fit much, much better in the lock. And so that's kind of what we're talking about when we say it's binding. So the key goes in there and it binds to the protein, and the more tightly it binds, the better the drug is, the more effective it's going to
Why
be,
is that? Why is
the
that?
less you're going to need.
Why is a better bound protein in the compound of the drug? Why does that make a better drug?
A lot of times it's because you need less of it, and so there's less chances for side effects, for it to hurt your liver or your kidneys or other things, because that's where a lot of the problems come up with the drug. You might have a great drug, but if you need to take so much of it that it's killing you, which is often the case in things like chemotherapy, then it's not such a great drug. So
it's efficiency then.
yeah, and in one aspect, yes, efficiency is a big important thing of it. There's a lot to it, but that's kind of a good way to think of it is you could take something that a drug that was maybe harmful, had a lot of bad side effects, and then make it more potent so that you need to take less of it, and then now the side effects are not as important. And so and a hydrogen atom, the placement of it can sometimes make or break that. It comes down to that fine of a
the placement in the development in the compound.
Yeah, so like
you're
the
working
three-dimensional location of it in space.
Yeah.
So sometimes it can move a certain way and let that key go into the lock just a little bit better, or it can move in a certain way and block the key and make it not work at all.
So you could also
and so it's really amazing that things are that finely tuned to where the one little tiny atom can make that big of a difference.
It's a statement of modern chemistry. It's what got you excited in the first place.
Yes.
It's
Yeah.
another world. It's a whole new world.
Right. It's a whole microscopic world.
It's the laws of physics in chemistry.
Right. 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 But applied to real human problems and helping people. That's
Yeah.
what excites me.
Yeah. So you're using the laws essentially of physics in chemistry to build drugs which are effective in medicine. And that's really fabulous. Yeah. And I'm sure you've seen, even in the past 10, 20 years, huge advances in this area.
Absolutely.
Yeah. So you're at the cutting edge now. So the proteins that you start working with, are they something that you choose, or are you looking in journals or looking in spec sheets, I guess, from big pharma companies? So we want to know about this one or that one. How do you make those choices?
So that's where I end up pulling all my hair out, trying to attack this problem. I invest an enormous amount of time thinking about what are the good proteins to work on. So we want to work on proteins that have a strong demand from a health perspective or from some other kinds of basic science perspective. But also at the same time, we need to work on proteins that are likely to succeed given our experimental needs. So proteins, for example, simple things, for example, it has to usually a smaller protein that easier for us to produce. We know that these proteins are more likely to make crystals. If we can't even make crystals of them, well, then we can't use this approach at all. Those are some considerations that we think about. And then there are some other types of considerations, more logistics and strategic considerations. Are there a lot of people working on this? Well, that's not as a good project to work on. We don't want to be in a direct competition with a lot of other labs.
Although you'd like to read what they do.
Yes.
Well, so, one day you're going to publish on this. And can you give us, as you can see down the path now, can you give us a sort of a general idea of what that article is going to say? I guess it's going to say something about locating the hydrogen atom.
Well, that's really what it is. And so what we'll do is actually, we just had a meeting about this last week. We will outline the method that we're developing, and what we will have in our publication is we'll have a number of benchmarks to assess how effective this method is, how accurate it is, what are the levels of false positives and false negatives, for example, and to also develop some guidelines so that other researchers can use this method for their own specific projects. Given their protein that they are studying, how likely will this approach work for them?
Exciting. So you're actually designing a methodology
Yes.
that the whole field can use in order to learn more about how these proteins work, how these atoms work, how these compounds work.
Yep.
That's so. And you think there's intellectual property protection down the pike on this, or is this just for the common good?
At this point, this would be because we're just looking at hydrogen atoms, and these are basic science principles that we're investigating. So I don't think there would be immediate IP that would come out of this, but perhaps 2 or 3 steps down the line, when we're applying these principles to specific drug target classes, and perhaps it'll help us to develop potential drug candidates, and where we have the advantage of this method, then intellectual property might play a role.
So this paper that we're talking about, the one you're going to submit to the journal Science, I don't know, where would you submit it?
We're still thinking about that.
Yeah. So I mean, would you submit it to more than one, or just the one you like?
Well, you're
best?
only allowed to submit to one journal at a time. So
okay.
we want to submit this to one of the top journals, but we still have to do a little bit more marketing research.
Okay, of course, marketing and science, sure. But it seems like to me, from what you say, is that okay, you write the paper. It's about the methodology of locating hydrogen atoms. Okay, it's published, and that's not the end of it.
Oh no!
In many ways, that's the beginning of it.
Right, that's the beginning.
Because you're going to go down. You're going to
Right.
find something you want
The
to
first
pursue.
the first
after
paper
that.
is just the proof of concept, and then after that we will further develop it and apply it to the important cases.
So how long have you been working on this particular investigation?
This is a offshoot of a project I worked on about 4 or 5 years ago when I was still at Berkeley. We were actually studying something else, and this was actually a side unexpected result that came from our work.
Okay, and I know you have what did you say 13 people helping now, something
Yeah.
like that. But are you also collaborating with other schools and other research scientists?
Oh,
elsewhere?
absolutely. That's very key to our work. We
Tell us
collaborate
about it.
with at least 4 or 5 or 6 different labs in Hawaii and on the mainland. National labs, for example, that provide us access to their accelerator facilities. We work with biotech companies that help us, where we're working together to characterize some of their drug candidates using these are some of our other projects in the lab. So this is actually just one out of about half a dozen different projects in the lab.
As the principal investigator, do you have to go get the money?
Of course. That's my
It's
job.
part of the job, eh?
Yes, that is my job. Yes.
So where's your funding coming from on this project?
So I'm very happy that to say that this project was just funded by a grant from the National Science Foundation. But primarily our research funding will come from the NSF as well as the National Institutes of Health.
Okay, we wish you well, Ho Leung Ning.
Thank you.
It's a wonderful project, and I usually I ask, why do I care? But I think I care a lot about this.
Oh, yes.
Better
Yeah.
drugs for everyone. So Ho Leung Ing and Cisco Jimenez from the College of Natural Sciences, a friend of SOES, the School of Ocean, Earth Science and Technology. Thank you very much for coming on our show and talking about locating the hydrogen atom.
Thank you for having us.
Thanks for having us.
Aloha.
Aloha.